These are the solutions to calculus homework number 22. So we have 4 problems here off the bat, just solving for t using natural logs. So question number 1, we have 5 raised to the t equals 7. So to use natural log, we'll take the natural log of both sides. So I'll have ln of 5 to the t equals ln of 7. Then I'll take this t and bring it down as a coefficient. So I'll have t ln of 5 to the t, no longer 5 to the t, just ln of 5 equals ln of 7, and then I'll divide both sides by ln of 5. So I'll have t equals ln of 7 divided by ln of 5. So we take this, plug it into our calculator, and we find that t will be equal to 1.209. Next question, number 5. We'll change colors. Next question, number 5. Set up similarly. So we have 50 equals 10 times 3 to the t. So this is like our exponential equations we've been working with. First, I'll start by dividing both sides by 10. So dividing both sides by 10 gives me 5 equals 3 raised to the t. Now again, I'll take the natural log of both sides. So ln of 5 equals ln of 3 raised to the t, and I'll bring that t down. So now I'll have ln of 5 equals t ln 3. Solving for t and moving it to the left side, we have ln of 5 divided by ln of 3. So we take this, plug it into our calculator, and we get t is equal to 1.465. So moving on. Number 10. So we have 10 is equal to 6e to the 0.5t. So for this, I'm going to start by dividing both sides by 6 to get the exponential by itself. So I have 10 divided by 6, which is 1.666667. So I'll just write that as 1.667 for now. Is equal to is equal to e to the 0.5t. So now I'm just going to take the natural log of both sides. So I have ln of 1.667 equals, on the right side we have ln of e to the 0.5t. So the ln of e goes away, and we're left with ln of 1.667 equals 0.5t. So now I'll just divide both sides by 0.5 and solve for t. So taking this, plugging it into your calculator, I get t equals 1.022. So now we have one more problem for this set, number 15. So 15 has 5e to the 3t set equal to 8e to the 2t. So this one's a little odd, but what we can do here is we can divide, see what we'll do. We'll divide both sides by 5 to start. So we'll have e to the 3t equals 8/5 e to the 2t, or I can rewrite that as 1.6 e to the 2t. And now I'm actually going to divide both sides by e to the 2t. So ignore this part in the middle. And we have e to the 3t over e to the 2t, and on this side, e to the 2t is going to cancel out. So on the left side, we have e to the 3t over e to the 2t, which is the same as saying e to the positive 3t times e to the negative 2t equals 1.6. So doing that, we actually have e now to the t, because when you multiply these two with the same base, you can add their exponents. So I have e to the t equals 1.6, so I can take the natural log of both sides. I'm running out of room. And what that leaves us with is t is equal to, I should say ln of 1.6. T is equal to the ln of 1.6, which, if we take and put that in our calculator, is 0.47. So question 21 has 4 different formulas, and we want to know in which town is growing the fastest, rather, which has the largest % growth rate. So we're going to start by noting the fact that k is equal to ln of a. And remember that we have P equals P initial times E raised to the KT. So for each one of these, we'll just find a value for K. So Ka is going to be Ka is equal to, Pa is here, so that's 0.08, which is equal to ln of A. Therefore, A equals E to the 0.08. So let's see, so that's E to the 0.08, which is 1.0833. And we'll do the same thing for the others. So we have KB is equal to negative 0.02, which is equal to ln of A. Therefore, A equals E to the negative 0.02. So A will be equal to 0.9802. For C, we'll have 0.03, which is equal to ln of A. Therefore, A is equal to E raised to the 0.03. So A is going to be equal to 1.0305. And then for D, we have KD is equal to 0.12, which is equal to ln of A. Therefore, A is equal to E raised to the 0.12. So that gives us an A value of 1.127. So at this point, we want to know which is growing the fastest. So out of all of these, the most positive A will give us the biggest R. So that means that D is growing the fastest. B asks us, which town is the largest now? So we're assuming that now is the initial population. So that would just look at the initial populations, in which PC initial is 1,200. So it's the largest to start. And then C asks us if any is decreasing in size, if so, which. So the only one that's decreasing in size is B, because it has an A less than 1. So it is decreasing in size over time. Question 22. So we have a population that is 1,000 and growing at 5% a year. Find a formula for the population at time t, assuming it grows 5% per year. So we'll start off, we'll say P initial is 1,000. So our R is going to be 5%, which is equal to 0.05. Therefore, our A is 1 plus R, so that means our A is 1.05. So our initial annual rate of growth is going to be P of T equals 1,000 times 1.05 raised to the T. And then for part 2, we want to turn that into a continuous annual rate. So we'll say K is equal to the ln of A, which would be the ln of 1.05. So K in this case is going to be 0.0487. We'll round it to that. And so our P of T is going to be 1,000, same initial, times E raised to the 0.0487T. So here are our two population functions. And then B says, estimate the population of the city in 10 years. So we're just going to take P of 10 for both situations. So we have 1, which would be 1,000 times 1.05 raised to the 10. So we take our calculator, and plugging this in, we get a population of 1628.9. We'll say there's a 0.9 of a person right now. And then for the other one, we'll say that P of 10, so this is our exponential, is going to be 1,000 times E raised to the 0.0487 times 10. So be careful when you put this in your calculator. So we take this, plug it into our calculator, and we get 0.0487 times 10, which gives us 1627.4. So these are very similar populations after 10 years. Question 31. So the population of the world can be presented as 6.4 times 1.0126 raised to the t. So using a continuous growth rate, we have, so this right here is our a, so we know that k would be equal to ln of a, so that's going to be equal to the ln of 1.0126. So take this, plug it into our calculator, 1.0126. We get a k value of 0.01252. And so we'll rewrite this, same initial population, 6.4, times e raised to the k, which is 0.01252, times t. Question 36 says, now we're starting with a different function. This time it's w in terms of t. So we have 32.4 times 1.036 raised to the t. And we want to find a formula using continuous growth rate again. So k is equal to ln of a, which is equal to ln of 1.036. So k will be equal to 0.03537. So then we'll rewrite this as w equals 32.4 times e raised to the 0.03537. Pardon me, this is too small to read. 0.03537 times t. And finally, number 40, we have the population of a city at 50% or 50,000 in 2008, growing continuous yearly rate of 4.5%. So give the population as a function of number of years since 2008. So we have initial population of 50,000. We have a continuous yearly rate of 4.5%, so that's 4.5 for k, which is 0.045. And so then we have an initial population or a population function that will look like 50,000 times e raised to the 0.045 t. So here's my function, and then if I sketch a graph of this, I'll sketch it off to the side. What will that look like? Well, we have population as a function of time, and our initial population at the year 2008 is going to be 50,000. So this is going to be our 50,000 in the year 2008. So really we shouldn't say 2008, we should say that this is 0. So this is years since 2008. And it will look something that goes like this. So you can find an additional point if you want. I'm not going to right now for the sake of time. B asks, what will the city's population be in the year 2018? So 2018 is 10 years since 2008. So we're going to say T is 2018 minus 2008, which is 10. So P of 10 is going to be 50,000, times E raised to the 0.045 times 10. So 10 years after 2008, we're going to have a population of 78,415.6. So maybe we'll just round that to 416. So we can have that up here. So this is going to be 10 years later, and this will be 78,416. So C is asking us to calculate the time for the population of the city to reach 100,000. This is the doubling time. So our doubling time formula, so our T2, is going to be the ln of 2 over the ln of A. So we need an A first. So our A is just going to be, or let's see, I guess I did this a little backwards. So we want to have k equals ln of a. Therefore, a is equal to e raised to the k. So this is e raised to the 0.045. So our a value is actually 1.046. So the time to double is going to be ln of 2 over the ln of 1.046. So the time to double will be, once we plug this into our calculator, 15.4 years. So it'll take 15 and a half almost years to double.